Our planet formed along with the other planets of our solar system from the protoplanetary disk that surrounded the young Sun around 5 billion years ago. The processes that formed our solar system still occur in our galaxy. New stars and planetary systems form from the remains of the old. Contrary to popular opinion, the space between stars is not empty. Gas and dust, remnants of the Big Bang and ancient novae, stars that shed parts of their mass, and supernovae, massive stars that explode, fill interstellar space with the raw materials to form the next generation of stars. As the galaxy rotates, the spiral arms sweep through space generating a bow shock wave. This wave collects gas and dust and concentrates it. Pockets of star formation result. The Orion Nebula is a region of active star formation located in the constellation Orion. Some stars as young as 500,000 years may be found here. Protoplanetary disks are flattened disks of dust, gas, and larger debris that maintain position with respect to the central mass due to angular momentum. Regions of instability in the disk, along with gravity, cause material to collect into larger masses referred to as planetesimals. The Kepler Space Telescope is one source of the discovery of new exoplanets. It specifically focused on a small patch of sky in the constellation of Cygnus, the Swan. It imaged this region for 9 years, from 2009 through 2018. The Spitzer Space Telescope uses infrared light to peer into the hearts of nebulae to uncover the secrets of star formation. As part of the NASA IPAC Teacher Archive Research Program, students from our school joined teachers and students from 3 other schools across the country and were given time on the Spitzer Space Telescope to investigate star formation in several dark nebulae, including the one shown here. This extrasolar planet is around a young star 2 million years old, in the Lupus star-forming region. It is one of the first planets outside our solar system to be directly imaged. Most extrasolar planets are detected by the effect they have on the light and motion of their star. A protoplanetary disk showing spiral arms due to its rotation. Also clumps of higher density are evident. The formal name for the process of star formation in the universe is the nebular hypothesis. The next few slides will walk you through how this works. A disturbance begins the process of collapsing a nebula into stars and planets. Disturbances include the shock wave from a nearby supernova explosion, the bow shock in front of a galaxy's spiral arms as the galaxy rotates, and magnetic field interactions. As a rotating cloud of gas and dust collapses, angular momentum is conserved by the cloud's rotation speeding up. This is much like a spinning figure skater whose speed increases when they tuck in, concentrating their mass in a smaller space. The central region of the disk has the majority of the cloud's mass and becomes a star. The flattened outer regions become planets. As the nebula continues to collapse, local regions begin to contract gravitationally on their own due to instabilities in the collapsing rotating cloud. These regions form planetesimals. These image is an artist's representation of a protoplanetary disk around a new star. Planetesimals in the solar nebula grew into protoplanets, and then planets, by a process known as accretion. Accretion is growth through collision and merger of smaller objects. Heat from the accretion of Earth, radioactive decay, and compression allowed molten material to sort into layers based on density differences. This led to the formation of Earth's iron core, a process often referred to as the iron catastrophe. Differentiation refers to the process of forming internal layers based on density differences. The most dense material, iron and nickel, sank to the center of our planet, forming its core. The most dense minerals sank to form the mantle. The least dense material rose and formed the crust. Seismic waves interact with the various internal layers in different waves. They reflect from and refract in these layers based on the layer's composition. Some waves will not pass through liquid, like the Earth's outer core. The complex behavior of these waves produces a snapshot of Earth's internal structure, similar to the way that ultrasound is used to image the insides of your own body. High-energy particles from the Sun, protons and alpha particles, and deep space cosmic rays are deflected from the Earth's surface by the planet's magnetic field. Our magnetic field protects Earth from much of the potential damage that could result from an impact of ACME, or coronal mass ejection, with the lower atmosphere. Damage includes loss of satellites, increased radiation exposure to air travelers, enhanced pipeline corrosion, and electrical blackouts.